Quadratic inequalities. Reminder, a quadratic equation when graphed will always be a parabolic shape. A quadratic equation is an equation of this nature, x squared plus 5x plus 6, usually equal to 0. A reminder again, y equals that is this parabola. And anytime that y is equal to 0, or plugging in y, or 0 for y, is how you find the x-intercepts. So if you wanted to relate this to what we just did, okay, when you're solving these quadratic inequalities, you're not going to be looking for where it's equal to 0, but you're going to be looking for usually where it's greater than or equal to 0, or where it's above the x-axis, or where it's less than or equal to 0, which would be below the x-axis. But like I said, we've already done these once this year. Just a reminder of how to do them. Where's the parabola above 0? Where's the parabola above the x-axis? So first step, what you do to find out where the parabola is above the x-axis, notice that it's a positive x squared. From what we did yesterday, anytime you have a positive x squared, it cups up. It's equal to 0 here and here. That's where it crosses the x-axis. It's above 0 everywhere to the right of there and everywhere to the left of here. Okay, it's not above 0 in the middle. So your answer will look something like this. Everywhere from negative infinity up to some point, including that point, and everywhere from that point up to positive infinity. So really the hard part is just finding out where those 2 points are. And all you have to do that, x squared plus 6x plus 8, not greater than or equal to 0, but set it equal to 0. That gives you your 2 intersection points. I would solve this by factoring. X and x, adds to give you 6, multiplies to give you 8, would be plus 2 and plus 4. Please do not forget to split that. Those aren't the answers. Your actual answers, x plus 2 equals 0, x plus 4 equals 0. Solve each of those, you will get negative 2 and negative 4. So that means my intersection points here will be negative 4. My intersection point here would be negative 2. Just a reminder of yesterday, we also talked about a parabola. All parabolas have axis of symmetries. If you look this one up, since that's negative 4 and negative 2, it's kind of obvious our axis of symmetry would be there at negative 3. So x equals negative 3 would be our axis of symmetry, which could be very easily found from this. Remember that negative b over 2a. That's how you find an axis of symmetry. Don't have to do it on this problem, just reminding you. Solve x squared minus 2x is greater than 8 and graph the solution set. First thing you need to do is we don't like greater than 8. We like greater than 0. So move that 8 over. Anytime you have a quadratic equation, make it equal 0. Or make it, in this case, greater than 0. So we're looking for where is this parabola. Here's 0. This is the x-axis. X-axis, same thing as your 0. That's, again, I told you, x-intercepts yesterday. X-intercepts, other names for x-intercepts would be roots or zeros. That's the reason we call them zeros, is because the x-axis is the 0 location. We're looking for where it crosses that x-axis. So where is it greater than 0? That's actually just like the last problem. Not greater than or equal to, so it's going to be greater than to the right of that and to the left of that. Do the same thing. We're going to factor. After we set it equal to 0, multiplies to give me negative 2, adds to give me negative 2, multiplies to give me negative 8. Good. So we got negative 4, positive 2. Set them each equal to 0, you're going to get x equals 4 and x equals negative 2. So this would be my negative 2. This would be my 4. So your solution set would be all values from negative infinity up to negative 2. I didn't put my union sign on that last one, but it would be union all the values from 4 to infinity. That is your OR statement, this set or this set. Last one of these. Where is it less than 0? Again, you have a parabola with a positive x squared, so it's going to be cupped up. We're wanting to know where is it less than that 0, which would be everywhere from... Here's where it's underneath 0, so everywhere from here to here. But you need the same thing. You've got to set it equal to 0. So first step, 2x squared minus 4x minus 9 equals 0. Let's just see if it will factor. Take the 2, move it to the 9. Let's try bottoms up factoring. X squared minus 4x minus 18. Can you think of any number that's going to add to give me negative 4, multiply to give me negative 18? 6 and 3, 9 and 2, 18 and 1. That's your list. Nothing works. So since it does not factor, let's use your quadratic formula. Here's the quadratic formula. Negative b plus or minus the square root of b squared minus 4ac all over 2a. Always do your discriminant first. B squared minus 4ac. You have b squared is 16 minus 4 times 2 times negative 9, I believe is a negative 72. 4 times 2, that's right. Minus minus is a plus, so your discriminant is equal to 88. And while we're at it, that discriminant is going to be under a square root. Let's go ahead and clean that up. I think we did this one the other day. This is the square root of 4 times the square root of 22. The square root of 4 times the square root of 22. There's going to be the square root part of your answer. So we have negative b. Let's plug it all in now. Negative b plus and minus the square root stuff over 2 times a is 4. Yeah, we did work this problem. Go through and you have 3 terms to reduce this. Let's divide everything by 2. 4 divided by 2 is 2. 2 root 22 divided by 2 is root 22. And on bottom, 4 divided by 2 is 2. That's your 2 answers. So where does that cross? This one is my 2 minus root 22 over 2. This is my 2 plus root 22 over 2. So if you want to write it in exact terms, my answer is going to be all values from 2 minus root 22 over 2 all the way up to 2 plus root 22 over 2. That's an exact answer. Okay, so here's your 2 approximate answers. 2 plus root 22. Be cautious. I'm glad I typed it in like this so I can warn you of something. Whatever you do, don't type it in as this divided by 2. Your calculator knows order of operations. If you type this in, it's going to do the square root of 22 divided by 2, and then it's going to add 2 to it. You want it to add that entire top, so if you want to type it in this way, make sure you do 2 plus root 22, hit enter first, and then divide by 2. So it's going to be about 3.3. That was the plus. And the minus would be 2 minus root 22. Enter, divided by 2, enter, about negative 1.3. So what values, when you plug it into this, would be less than 0? You should be able to plug any of these. You should be able to plug in all the values from negative 1.3 up to 3.3, and it'll give you something less than 0. First application problem for quadratic equations. 100 meters of fencing will be used to fence in a rectangular region. Then what dimensions for a rectangle will maximize the area of your region? And you would think that if you use 100, let's say feet instead of meter, just because that makes more sense to us. You would think if you use 100 feet of fence, you get the same size area, but you don't. Let's say you used a 40 foot by 10 foot fence. That would add up to all your 100, in this case meters or feet, whatever you're working with. 40, 10, 40, and 10, that's all of your fencing. Or if you had a 25 by 25, that'd use all your fencing. Or if you had a 30 by 20. That's just 3 scenarios that would use all 100 meters of fencing. But look what happens. If you have a 40 foot or 40 meter by 10 meter fence, you have 400 square meters of area fenced in. If you have a 30 foot or 30 meter by 20 meter, you have actually a 600 square meter area fenced in. If you have a 25 by 25, you have a 625 square meters. So all depending on what what shape you build, the same amount of fence actually fences in bigger and bigger regions or smaller regions. Okay. If you could somehow figure out how to do it, that would be how to maximize area. You don't see many circular fences. That'd be really hard to build a circular fence. But that's how to actually maximize your area, because if you had 100 meters of fencing, I'm not going to do that, but let's say that'd be the circumference is 100. You could divide that by, let's see, circumference is pi times diameter. If you divide that by pi, that would give you the diameter of that circle. If you half that and do pi r squared, well, I've got to do it now. I've talked too much about it. Let me show you how much area that actually fences in. If your circumference is 100, 100 divided by pi, that's your diameter, divided by 2, that's your radius. It'll be about 15.9 meters. If you square that radius and multiply by pi, that gives you the area. That's 795 square, in this case, nearly 796 square meters, as opposed to, look at these areas, 400, 625, 600. That's a whole lot more area if you could somehow build a circular fence. But again, that'd be really hard to do, because I think you have to use fence post, and it's really hard to curve your barbed wire. But anyway, back to the actual problem at hand. Here's how we're going to work this. If you want to build some sort of rectangular fence, and we want to use all 100, well, think of it like this. The rule is try to use as few of variables as possible. To keep from confusion, use as few of variables as possible. So here's what I'm going to do. Since I have 100 feet of fence, does everybody understand that 50 feet of it, or excuse me, meters, I keep saying feet, 50 meters of it will be used for these two sides. So what if I use X meters of it here? If I use 20, that would leave me with 30. If I use 10, that leaves me with 40. If I use 5, that leaves me with 45. If I use 1 meter here, that leaves me with 49. I'm finding this other side by doing 50 minus whatever this is. And you will have to set one up like this on your test. So 100 meters of fence. If you add X and 50 minus X, actually the X's cancel, and it leaves you with 50. So 50 was used for these two sides, 50 would be used for these two sides. You've used all 100 meters of fence. We want to maximize area. Well, let's write an area as a function of this X, A of X. To find the area of a rectangle, you'll always do length times width. So that will be X times 50 minus X. And if you multiply that out, A of X, or A, is equal to, let's do negative X squared plus 50X. Let's just flip-flop those two around. That's my function for area, and all depending on what I choose for X. If you let X be 1 or you let X be 2 and you plug it into this, you've actually got the area of this now. So we want to make this area as big as possible. Let me see what I've got behind this yellow box. It's just going to be curious. Okay. Yeah, that's what I thought. They actually didn't use X's, they used L's, which is fine. Just imagine those were X's instead of L's. And here's what you've got is a picture of what this area function would look like. If you let your X value be 10, and you can go up, you'd have an area close to 300. Let your X value be 20, you've got an area close to about 550. But if you want the maximum area, what you need to know that if this is my X values, this is my area values, or my Y values usually, you want the top Y value possible, guys. That always occurs at your vertex. So pretty much all we're looking for in this problem is what's our vertex. So here's how we're going to find it. Didn't I give you a formula? If it's in this form, if you ever just need a vertex, that's negative B over 2A. And I'm actually going to go into some calculus here in just a second. That for some reason that's not writing good on that yellow. So negative B over 2A, this is plus 0. You don't have a constant term over here. So here's your B term and here's your A term. Negative 50 over 2 times negative 1 gives you 50 over 2, which is 25. That is the X value of your vertex. What does that X value mean? That is the x value that will maximize, because that's the highest point on your parabola. That's the x value that's going to give you the maximum area. And again, this was an XA problem, not an XY like normal. And if you plug this 25 in, it'll actually tell you what that maximum area is going to be. I think it's, let's see, that'd be negative 625 plus, let's see, 1250. I'm going to have to type it in. Let me pull that over here. Let me show you another function, just while we're at it, of your graphing calculator. If you ever have, which we don't here, but if you ever have multiple values that you need to type in, or to plug in, watch this. Negative x squared plus 50x, you can just graph that. Let me change my window. Let's go from 0 to, I think it was about 30 is what they had there. No. Let's go 0 to 50 on my x's. Let's do 0 to 1,000 on my y's, and let's scale my y's by 100. Pretty good graph. If you ever need to plug lots of things in, and you could do this on this problem, what x value is going to maximize area? You have this trace button right here. Well, that's pretty cool. It automatically went to the vertex. If you want to plug in any number, use that trace button. You could plug in 30. Plug in 30, you get 600. That'd be your area. Plug in 20, actually the same area. Plug in 25, which is what we need, and it gives you that x-y combination. So when you have an x value here of 25, you have an area of 625. That's going to be the x value that maximizes area, and this will be your maximum area. If you are building a rectangular plot of land here. Maximum height of a football. If a football is kicked straight up, I don't know why you would want to kick a football straight up, but if you ever kick a football straight up with this initial velocity from a height of 5 feet, then its height above the earth is a function of the time given by this function. At any time, you can tell how high the football is by plugging it into that function. What is the maximum height? Again, notice the negative 16t squared. Once you get, if y'all have not taken physics, or have you taken physics? So you've seen these functions before, right? This negative 16t squared is actually, that comes from gravity. That's where that constant comes from. It's negative 32 meters per second squared, correct? It's the acceleration due by gravity. That's where that negative 16t squared plays into this formula. Y'all knew that, right? Where's the plus 5 came from? That's how high you kicked it from. Where does the 128 come from? That's your initial velocity. I think, let's see, the actual form, you don't have to write this down, negative 16t squared plus v0t plus h0. Isn't that the formula? That's the one you learned in physics. To where v0 is your initial velocity, how hard you kick it or throw it. h0 is your initial height. So, with all that said, what is the maximum height? This is an upside down parabola. Kicked from 5 feet up, so it'll look something like, well, actually no. To where that would be your XY axis. So it's kicked from an initial height of about 5 feet. We want to know how tall is it going to get. All they're asking for is what is the vertex. That's it. So all you've got to do to find the vertex, since it's in standard form, is negative b over 2a. So that'd be negative 128 over 2 times negative 16, which is negative 32, which gives you 4. But being able to interpret that, that's the problem. This function is a function of t. It's t, comma, h. To where your inputs are time in seconds, your h is your height. So what is this for here? That's your, what's normal, your x equals negative b over 2a. It's not x here, it's t. So t is 4. That's not the height. It says what is the maximum height. So be cautious what you're looking for. Since you're looking for height, you're going to have to take this 4 and you're going to have to plug it in to find your height. So what that says is it reaches its maximum height after 4 seconds, but how tall is it? So you're going to have to do negative 16 times 4 squared, which is negative 256, plus 128 times 4, which is 512, plus 5. So that'd be 512 minus 256 is 256, plus 5 is 261 feet. That is how tall that ball is kicked. Wow. He boomed it. Next section. Students will use synthetic division and the remainder theorem to factor polynomials. They will combine this knowledge with other theorems to find zeros of polynomial functions. We've done some of this. Okay. Reminder about synthetic division. Here's what synthetic division was used for. X squared plus 6x minus 3 divided by x plus 2. It's just a basic synthetic division problem to remind you. You have the box, and inside the box, Henshaw, remind me, what do I put? Not 2, but negative 2. You always put the opposite. Remember that? If you set this thing over here equal to 0, move the 2 over, that's what you would put in the box. Next to the box, you have, let's see, Avery, do you remember that? What 3 numbers will I have next to the box? Good. 1, 6, negative 3. We draw a line underneath. Bring down the 1, multiply, add the 2 together, multiply, add the 2 together. The last number was your remainder. Since you're dividing x squared stuff by x stuff, anytime you divide x squared stuff by x stuff, perform that operation, I believe you get x stuff. So what you can do is this 1 will represent your x stuff, this 4 will represent your constant, and whatever's in the box is your remainder. So we're going to do minus 11 over whatever you divided by. So that's how you use synthetic division. You didn't have to do minus 11 over. You could also do plus negative, which is the same thing as minus. You could have wrote that either way. So that's just a reminder about what synthetic division is. Here's another one. We're dividing by x plus 4, so we put a negative 4 in the box. If you have x to the 4th, that'd be 1x to the 4th. But notice something. It skips from x to the 4th to x squared stuff. You must put a 0 in the place of x to the 3rd stuff. There's no x to the 3rd, so put the 0. So you have 1x to the 4th, 0x to the 3rd, negative 14x squareds. You have 5x's, and you have minus 9. Flying through this one. Bring it down, multiply, add. That's your steps. Bring it down, multiply, add. Brought it down, multiply, add. Multiply, add. Multiply, add. You divided x to the 4th by x, so you're going to get x to the 3rd stuff. So that's be 1x to the 3rd minus 4x squared plus 2x minus 3. The last number would be your remainder. Take your remainder, write it over what you divided by. Not negative 4, but x plus 4. Any questions? No. I'm going to take you a second, give you a second to try this. This is called the remainder theorem. What I want you to do is I want you to take x to the 3rd plus 2x squared minus 6x plus 3. And I want you to try to plug in 2. Let's say that x is equal to, I'll give you all a second, plug that into that and see what you get. So we plug it in, we get 7. Let me show you some, and don't even ask, I have no idea why this works. Okay, what I'm about to show you is it's still magic to me too. Okay, use synthetic division. Put the number that you're trying to plug in the box. 1, 2, negative 6, 3. And honestly, I'm pretty quick at synthetic division, and there's a good possibility what I'm about to show you I can do quicker than just plugging it in. And there's a reason this is called the remainder theorem. Watch. 1, 2, 4, 8, 2. Hang on. Did I mess up somewhere? 1, 2, negative 6, 3. X to the 3rd, x. That's right. Bring down the 1, multiply, add. 4 times 2 is 8, 2, 4. No, that's right. 3 and 4 is 7. Which is what you got when you plug that in. Another way of plugging values into functions, to polynomial functions, this only works for polynomial functions, is by performing synthetic division with that number. the remainder that you get is what you would actually get if you plug that number in. You can test it again, plug in, put a 4 here, and plug in 4 and see whatever that remainder is what the value would be when you plugged in 4. So here's how we're going to use that. We want always, if possible, we want a remainder of 0. We want to think, okay, when I plug this in, that's the remainder that I would get. Okay, or that's the y value that I would get. Because when you have a y value of 0, guess what? Where do I have y values of 0? Here, 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 and here. Anytime you run up on y values of zeros or no remainders, you have factors at those points. But this remainder theorem, we're going to actually use this a good bit. So commit that to memory. The number that you plug in, the remainder that you get would actually be the y value that you would get when you plug that x value in. So if you graphed y equals this, if you plug in 2, you're going to get 7. This 0.27 would be on that graph. Okay, let's do some more of that. Use the remainder theorem to find p of 3. So pretty much we're saying plug 3 into this. Do we have to use the remainder theorem? On your test, if you don't use the remainder theorem to do this, would I know it? No. All we're asked to do is plug 3 into that. I am going to do it using the remainder theorem. If you want to do it the other way, that's fine, just to check us. So we're going to plug in 3 into 2x to the third, negative 5x squared, plus 4x minus 6. Bring it down, multiply, add, multiply, add, multiply, add. P of 3 is 15. When you plug 3 into this, you should get 15. Okay. Now we're going to use what we just learned to factor polynomials, and this will be the last thing we do today. Determine whether x plus 4 is a factor of p of x equals x to the third minus 13x plus 12. If it is a factor, then factor completely. Let me, one more time, let me explain factors. Back when you were in 7th and 8th grade, you did factor trees. A factor is something that a number can be broken into. 2 and 4 are both factors of 8 because in this factor tree I could break 8 into 2 and 4. And since that is true, I know that if I divide 8 by one of them, I'm going to get the other one. 8 divided by 4 is 2, 8 divided by 2 is 4, and it goes a step further. When something's a factor of 8, and I can break it down into those two values, that means I can rewrite 8. I could rewrite 8 as the product of its factors. That process is called factoring. So anytime you divide something by another number and you get a remainder of 0, that's vital. Anytime you divide and you get a remainder of 0, that means that that value is a factor along with this value as well. And we can rewrite that in terms of those two. That's what we're doing here. We're going to see, is this a factor of this? The way we're going to do that is by using synthetic division. Is x plus 4 a factor of 1x to the third plus 0x squared minus 13x plus 12? Bring it down, multiply, add. Multiply, add, multiply, add. And we see, yes, that is a factor. Anytime you get get a remainder of 0, that means that x plus 4 was definitely a factor of this. But here's the important part. I just divided, let me write it in blue. I just divided x to the third minus 13x minus or plus 12. I divided that by x plus 4, and I got x squared minus 4x plus 3. Since this divided by this is equal to this, I can rewrite x to the third minus 13x plus 12. The same way that since 8 divided by 4 was 2, I could rewrite that as 2 times 4 is 8. I can now rewrite this as x plus 4 times x squared minus 4x plus 3. But notice it says this, factor completely. I factored one step. So do I have to do that again? No. Because you know how to factor pretty much, hopefully. You know how to factor x squared stuff. So I can factor x squared minus 4x plus 3. That's not a problem. I have issues factoring x to the third, x to the fourth, x to the fifth. Okay, I'm going to use this synthetic division stuff to factor big stuff like that. But once I get it to this point, x plus 4 times that, I can leave the x plus 4, and I can break down x squared minus 4x plus 3 by doing x times x, and ask myself what two things add to give me negative 4, multiply to give me positive 3, and that would be a negative 3 and a negative 1. While we're on the subject, I do want to point something else out, though, before I give you your homework. Let's graph, because this is the connection I want you to start making. If you make this connection that I'm about to show you, this chapter honestly will be pretty easy to you. Let's graph x to the third minus 13x plus 12. Graph, and I need to do zoom standard. Zoom 6. And notice on this x to the third graph, you've got the graph starts down here, it increases, it hits some point up here, it doesn't really matter where, then it starts decreasing, it comes down here, hits some other point, and it starts increasing. Something I will point out about these polynomial graphs, you can always draw, they're continuous functions. There's no x value you can't plug in. You can always draw these things without lifting your pencil. So it's a smooth function. But what I want to point out is these three values. I'm getting ahead of myself, but that's fine. How do you find how do you find x-intercepts? You plug, this is y equals, right? How do you find x-intercepts? What do you think, Carly? How do you find the x-intercept of a function? Plug in what for what? Find the x-intercept, you plug in 0 for y, not x, right? To find a y-intercept, you plug in 0 for x. To find an x-intercept, you plug in 0 for y. So let's plug in 0 for y here. Instead of y equals that stuff, let's make that stuff equal to 0. Does everybody see that there's three different values of x-intercepts there? Which would be negative 4, 3, and 1. That, you'd have to split it and set this equal to 0, set this equal to 0, set this equal to 0. Look at your graph. Do you see the connection? This thing factored into x plus 4, x minus 3, x minus 1. Here's the graph of that function. And it looks like that graph crosses at negative 4. That graph crosses at 1, and that graph crosses at 3. We're about to use graphs to factor. Okay, this is going to be a valuable tool, and you're going to be using the graphing calculator a lot this chapter. We're going to be using this to actually figure out how to break down x to the third, x to the fourth, x to the fifth stuff functions.